Welcome to the Arduino Programming for Absolute Beginners course. In this video, we'll start from scratch and introduce you to the fascinating world of Arduino and programming. Whether you are a complete beginner or have some basic knowledge, this course will provide you with a solid foundation to begin your Arduino journey. Let's begin with an overview of Arduino and its applications. Arduino is an open-source hardware and software platform designed to simplify the process of building electronic projects. First, let's start with the hardware. It consists of a circuit board called Arduino board. This board is the heart of any Arduino project. And the best part is that its design is open source. This means you can freely access and download the design files to understand how it's actually made. So you have the freedom to experiment, learn, and create projects without any limitations. Now, let's discuss the software aspect. The program that controls and runs the Arduino board is called the Arduino software. It is also called Arduino IDE, which stands for Integrated Development Environment. This user-friendly software enables you to write, compile, and upload code to the Arduino board. The great news is that the Arduino software is also open source and completely free to download from the Arduino website. Now, let's take a closer look at the Arduino board itself. There are different types of Arduino boards available, but they all have one element in common: the microcontroller. You can think of it as a small computer on a single chip. It's like the brain of the Arduino board. Although different Arduino boards may have different types of microcontrollers, but their main purpose remains the same. The main purpose of the microcontroller is to run your code and control the connected hardware. The most commonly used microcontroller in Arduino boards is the Atmega 328P. It has digital input-output pins, analog pins, and a range of other impressive features. To provide easy connectivity, the pins on the microcontroller are directly connected to the sockets on Arduino board. These sockets are called headers. Headers simplify the process of connecting external devices and modules to the microcontroller, without the need of any soldering. They also allow us to connect additional circuitry to the Arduino board quickly and easily when prototyping with a breadboard. Breadboard plays an important role in making prototype your circuits. It allows you to experiment with various electronic components and connections before making any permanent circuit. You can easily link the breadboard circuits directly to the microcontroller, using the headers on the Arduino board. The headers have been arranged around the board and labeled for easy to use. They are divided into three main groups: digital pins, analog input pins, and power pins. Each group of pins provides some special functions. Let's begin with the digital pins. Arduino Uno board comes with 13 digital pins. Think of these pins as the on-off switches of the Arduino. These pins are used to send and receive digital signals. Digital signals have only two states, either off or on. In electrical terms, off state represents 0 volts, while on state represents 5 volts with no intermediate values. This simplicity makes digital pins perfect for various tasks, such as reading button presses, controlling LEDs, and communicating with other digital devices. Next, Arduino boards features analog input pins. Unlike digital pins that handle just on-off signals, the analog pins can work with analog signals, which provide a continuous range of values between 0 and 5 volts. This feature is especially useful when dealing with sensors that produce varying voltage levels. For example, temperature sensors, light sensors, and many others fall into this category. Can we use analog input pins as digital input-output pins? There is a common misconception that analog input pins cannot be used as digital pins. But in reality, this is not true. All 6 analog input pins on the Arduino can be used as digital input-output pins. So, in total, you have 19 digital pins available to work with. This flexibility allows you to connect additional digital devices to your project. You might have noticed that there are no pins labeled as analog output pins. However, in reality, there are analog output capabilities hidden among the digital pins. If you take a closer look, you will notice that some of the digital pins are labeled with the tilde symbol. These pins are called PWM. PWM stands for pulse width modulation, and it is a clever technique that allows you to simulate analog output using digital pins in a highly effective manner. Although these pins are technically digital, but they offer a unique way to control various aspects of your projects, such as controlling the speed of the motors, dimming LEDs, and create smooth fading effects as if they were actual analog output pins. Lastly, the power pins provide a stable and reliable electrical supply for the Arduino and all connected components, ensuring your projects run smoothly. The Arduino can be powered using different ways. One way to power the Arduino is by using the USB port. You can connect the Arduino board to your computer using the USB port. This allows you to upload code to the Arduino and also test your projects. It's a convenient option when you are working with the Arduino and your computer together. Another option is to power the Arduino with batteries or an external power supply. This method is useful when you want to use the Arduino independently, without connecting it to a computer or USB power source. To power the Arduino this way, use the DC barrel jack on the Arduino board. Make sure to provide a voltage between 7 to 20 volts. However, it's recommended to use a 12-volt power supply when using the DC barrel jack. There's a lot more to explore with the Arduino board. But for this course, this information is enough to begin your Arduino journey. To write and upload code to the Arduino, you'll need a software tool called the Arduino IDE. There are different versions of the Arduino IDE available on the official website. However, for this course, we will use Arduino IDE 1.8. It is a beginner-friendly software tool and works well with any Arduino board. It provides a simple platform for beginners to get started with coding and uploading code to the Arduino boards. You can find the download link on the right side. Make sure to choose the correct version for your computer. Click on the download link that matches your computer's operating system. The download will start automatically, and the file size is relatively small, so it shouldn't take too long. Now, open the downloaded file to start the installation process. The installation process is straightforward and user-friendly. Just follow the on-screen instructions, and you'll have Arduino IDE installed in no time. After installation is done, you can launch Arduino IDE from the Start menu or the Applications list. Now the Arduino IDE is installed and running. So navigate to the Files menu. From the drop-down menu, select Preferences. In the Preferences window, first, increase the font size a little bit to make the code more readable. Next, let's enable line numbers to help you keep track of your code. You simply select Display Line Numbers checkbox, and the line numbers will appear on the left side of the Arduino IDE. Now, let's talk about the path setting. This is the location on your computer where your code will be stored. So whenever you save your code, it will be stored in this location. You don't need to worry about the other settings for now. Simply click the OK button to apply the changes you have made. Next, it's time to connect your Arduino board to your computer using a USB cable. Make sure your board is powered on. If you will see the green LED indicator, it means the Arduino is powered on. Now, you are ready to upload your first program onto your Arduino. Before you upload the program, you need to tell the Arduino IDE what kind of Arduino you have. So, go to the Tools menu. And then go to the Boards option. Here, you will find a list of supported Arduino boards. Simply choose the one you have. For example, I will select Arduino Uno. The last step before programming is to tell the IDE on which COM port your board is connected to. So again navigate to Tools, and then go to the Port option. As you can see, the Arduino board is connected on COM port 5. You just select the COM port, and you're good to go. Now we are ready. Let's make sure that everything is working as expected. First, navigate to the Files menu. From there, go to the Examples. Here, you will find a collection of code examples to perform various operations. You can try it yourself. From the Basic section, you just open the Blink sketch. This is a simple sketch that blinks the onboard LED. The Arduino have an LED connected to the pin 13. And we are going to blink this LED. Before uploading the sketch to the Arduino board, let's ensure there are no errors in the code. You just click on the Verify button, and Arduino IDE will check for any mistakes in the code. If everything is correct, you will see a Done Compiling message in the bottom status bar. If there are any errors in the code, the error message will be displayed here. Now, it's time to upload the code to the Arduino board. You just click on the Upload button, and Arduino IDE will transfer the code to the Arduino board. As you can see, the onboard LED start blinking. It means everything is set up perfectly. Now we have tested our setup and it works fine. So let's dive into programming. First, open a new sketch in the Arduino IDE. Here you can see, a program with some code is already written for you. A program is just a set of instructions, and it performs specific tasks, such as turning on an LED, or driving a motor. In the context of Arduino, a program is also called a sketch. Arduino uses the programming languages C and C++, which are the most widely used languages of all time. These are extremely powerful and versatile languages. However, programming in C or C++ can be a bit challenging for beginners. The good news is that Arduino follows a structured programming approach, which provides you a well-defined way of writing a program. Let's take a closer look at the basic structure of an Arduino sketch. An Arduino sketch is divided into two main parts, void setup and void loop. These functions are very important and must be included in every Arduino sketch. Without these functions, the sketch will not compile, and it will give you an error message. Let's see what happens when we try to compile the code without the setup function. The Arduino IDE will show an error message in the console. It reminding us the importance of having the setup and the loop functions. It is important to note that every Arduino function has its own name. For example, the name of this function is setup. If you notice, the color of the void setup function is orange. This color indicates that the Arduino software recognizes it as a built-in function. However, if we change the case of the setup function, then you will notice it turn into black color. This means that Arduino doesn't recognize it anymore. The reason for this difference is that the Arduino code is case sensitive. So always use correct case, otherwise the program will give you an error message. This is an important point to remember, especially during late-night coding sessions. The code for each function is written within curly brackets. It is called the body of the function. The opening curly bracket indicates the beginning of a function, while closing curly bracket indicates the end of a function. It's required to have matching sets of curly brackets for each function. If you miss one of the brackets, then the code won't compile, and you are presented with an error message that looks like the one shown in the console. The setup function is an important part of an Arduino program, and it runs only once during startup. This means any code written inside this function will execute just once. So this function is perfect for setting up initial configurations or performing tasks that need to happen only once. The next function is the loop function. This is also highlighted in orange, so the Arduino software recognizes it as a built-in function. Instead of setup function which runs only once, the loop function runs over and over again. The code written inside this function runs continuously until you press the reset button on the Arduino board, or you just remove the power. Inside setup and loop functions, you will notice some text written in gray. These are comments. Comments are written in plain English and provide explanations about the code. The Arduino software completely ignores comments during compilation and uploading, so they won't affect how the code runs. This comment is started with the double slashes symbol. It means it is a single-line comment. Single-line comments are perfect for adding short explanations to a specific lines of code. There is also another type of comment called multi-line comment. Multi-line comment starts with a slash, followed by an asterisk symbol, and ends with an asterisk symbol, followed by a slash. Multi-line comments are used when you need to add more details for the code that expand to multiple lines. Comments are helpful to improve the readability of the code. When someone else reviews the code, clear comments can help them to understand the logic and purpose of each section of the code. Alright, now we have covered the basic structure of an Arduino program. Now, we are ready to dive into writing our very first Arduino code. As you know, Arduino comes with a built-in LED, which is connected to pin 13. Our goal is to create a simple sketch that makes this LED blink. The first function you will need is the pin mode function. This function allows you to configure a specific pin on the Arduino board for either input or output. I have used pin mode function inside the setup function because it needs to run only once when your program starts. You'll notice the word pin mode is highlighted in orange. As I mentioned earlier, it tells you that Arduino already knows about this function. If you look at the case of the pin mode, the letter M is written in uppercase, and there are no spaces in the function name. This is known as camel case style, where the first word is in lowercase, and the first letter of each next word is capital. For example, digital read, analog write, and so on. So the pin mode is written in camel case to follow the standard naming conventions in Arduino. It's not only increase readability of the code, but also ensures that Arduino recognizes and interprets these functions correctly. This function needs two parameters. The first one is the pin number. This is the pin number on your Arduino board that you want to configure. For example, the onboard LED is connected to the pin 13, so if you want to control the LED, you'll set the pin number as 13. The second parameter of the pin mode function is called mode. This parameter indicates how you want to configure the pin. There are two options you can choose from, input and output. If you set the pin as an input, it means the pin can receive signals from external components like sensors. This is perfect for gathering data from the outside world. On the other hand, if you set the pin as an output, it allows you to control external components like LEDs or motors. In our case, since we want to control the LED, so we will set it to output. Notice that the word output is written in uppercase, and the color is blue. Whenever you see uppercase words in blue, it means they are predefined constants in the Arduino language. We will explore more about constants in the upcoming sections. That's all you need for setup. Next, moves on to the loop function. The first function you will need here is the digital write function. With this function, you can send a digital signal to a specific pin. The orange color tells that the Arduino already knows about this function, so we are in good hands. This function needs two parameters. The first one is the pin number. This is the pin number on your Arduino board that you want to control. In our case, the pin number will be 13. Now, let's talk about the second parameter, which is called signal value. It can be either high or low. As we have discussed earlier, the digital signals have two states, either off or on. In electrical terms, these can be referred to as either a high or low value. Since the Arduino Uno requires 5 volts to run, so the high value is equal to 5 volts, and low value is equal to 0 volts. So, we will set the signal value to high. It will send 5 volts to the pin 13, which is enough voltage to turn on the LED. So, with just a single line of code, we can light up the LED connected to pin 13. Next, we will add a delay of 1 second. The delay function stops the program for a specified amount of time in milliseconds. In our case, the value is 1000 milliseconds, which is equal to 1 second. During this time, nothing happens, and the LED remains on. After the delay, we use the digital write function again. But this time, we will set the signal value to low. This statement tells Arduino to send 0 volts to pin 13, which will turns the LED off. Finally, we will add another delay, to keep the LED off for 1 second. Since this code is placed inside the loop function, so it will run over and over again, and it will give you the blinking effect. Before you upload the code, let's cover one more important concept. You'll notice that each line of code ends with a semicolon. The semicolon plays an important role in the C language. The semicolon tells the compiler about the end of the statement. It's like a full stop in a sentence, which tells the compiler where the one statement ends, and the next one begins. If you forget to include the semicolon, the compiler might get confused, and show errors when you try to compile your code. So, to keep your code running smoothly, always remember to include a semicolon at the end of each statement. Now, let's upload this sketch to the Arduino board, and see the magic of the blinking LED in action. As you can see, the LED is now blinking just as we expected. It shows the code is working fine, and our LED is dancing like a disco star. How cool it is! But remember, this is only the beginning of your Arduino journey. Let's take a closer look at the code, and understand how the microcontroller runs it. When you power on the Arduino, the program starts running. It begins by entering the setup function. It executes the instructions one by one, ignoring any comments. In our case, there is just one instruction, which sets pin number 13 to output. This tells the microcontroller that we want to interact with external components, like LEDs. After executing the instruction, there is a closing curly bracket. It indicates that the setup function ends here. As the setup function runs only once, so the microcontroller moves on to the loop function. Inside the loop function, the microcontroller repeatedly executes the instructions to create the blinking effect for the LED. The first instruction tells the microcontroller to send 5 volts to pin number 13, which lights up the LED. The next instruction tells the microcontroller to wait for 1 second. The microcontroller follows this instruction and waits for a second. Then, it moves to the next instruction, which tells to send 0 volts to pin number 13, which will turn off the LED. And once more, it waits for 1 second. After this, we have a closing curly bracket. It indicates the end of the loop function. Now, the microcontroller goes back to the start of the loop, and repeats the instructions from the beginning. There you have it. The beauty of the code lies in its simplicity, that keeps everything running smoothly. I have used TinkerCad to create the code simulation. TinkerCad is a powerful online tool that offers a user-friendly environment to design circuits and it provides a simple tool to write code for Arduino boards. TinkerCad has everything you need, including sensors and a breadboard, making it perfect for beginners to experiment and learn. TinkerCad also provides a built-in code editor. It is fully compatible with the Arduino IDE. You can simply paste your code here and run it by clicking on the Start Simulation button. TinkerCad comes with a powerful built-in debugger that will take your learning experience to the next level. You can debug your code by adding breakpoints on specific sections of your code. Breakpoints allows you to stop the program's execution and examine what's happening. Let me show you how they work. To set a breakpoint, simply click on the left side of the line where you want to pause the code. This blue indicator tells that the breakpoint is active for this line. Now, let's see it in action. So, click on the Step Over button to execute the code line by line. This incredible feature makes it easy to understand how your code behaves at each step, which is extremely valuable for learning and troubleshooting. So we will use it a lot throughout the course. Now, let's move on to the next section. In this section, we will create a simple LED chaser using an Arduino. Take a look at the wiring diagram. Here, I connected 6 LEDs to the Arduino, with each LED connected to pins 8 to 13. The code for this project is very simple. In the setup function, first we will use the pin mode function to set all 6 pins as output. Since the first LED is connected to pin 8, so we will set pin 8 as an output. And then, we will repeat the same process for the other pins. To avoid rewriting the code multiple times, we will duplicate the same code. And then, simply adjust the pin numbers where the LEDs are connected. Remember, the LEDs are connected to pins 8 to 13, and we have set all these pins to output. Now, let's move on to the loop function. Here, we will use digital write function to turn on all the LEDs together. For example, we will turn on the LED connected to pin 8 by setting its signal value to high. Then, we will repeat this process for other LEDs by setting up their pin numbers. To create a blinking effect, we will add a delay of 300 milliseconds after turning on all the LEDs. This delay will keep the LEDs on for 300 milliseconds. After the delay, we will turn off all the LEDs by setting their signal values to low. Finally, we will add another delay of 300 milliseconds. It will keep the LEDs off for 300 milliseconds. Now, let's test the program to see if the LEDs blinking correctly. As you can see, the LEDs are blinking just fine. Let's move back to the code. To make the code more organized, we will add a comment line to separate the code for the two patterns. Now, for the second pattern, we want the LEDs to turn on one by one, and then turn off one by one. This will create a cool LED chaser effect. To achieve this, we will add a delay of 300 milliseconds before turning on each LED. This delay will give the appearance of LEDs chasing each other. After turning on all the LEDs, we will turn them off in the same sequence and with the same delay of 300 milliseconds. Instead of typing the exact same code over and over again, I am reusing the same code that we write earlier. This trick helps you to write code quickly and saves your time and efforts. Now the code is ready. We have added two LED chaser patterns inside the loop function. Let's give it a try by uploading it to Arduino. As you can see, the LEDs are blinking with both patterns, all LEDs turning on together, and then chasing each other in a sequence. The coolest part is that, we have only used two functions to create these patterns, digital write and delay. By using these functions in different ways, you can make really cool LED patterns that chase each other. However, if you keep adding more patterns directly into the loop function, it can get really long and messy. It becomes hard to handle all this code, and it is always difficult to make changes in the large code. To solve these problems, the C language has a simple solution called functions. Functions are like the building blocks of your code that make your life easier. They help us to keep our code neat and organized. You can make the functions in two simple steps. First, create a function. And then, call the function. Let's get started by creating a function. It's actually quite easy. Just copy the setup or loop function from a blank sketch. And then, paste it into your code. After that, give the function a new name. You can choose any name you want. When naming functions, always use a name that describes what the function does. I have named this function as blink all LEDs because it says exactly what the function will do. Remember, blank spaces are not allowed in the function names. Let's understand where you can put your functions in the code. There are two suitable places in your code to put your functions. You can either place your functions above the setup function or below the loop function. The choice is entirely yours. No matter where you put the function, the working of the function remains the same. Next, let's add some code into our newly created function. We will not write any new code for this function. We have already written some code in the loop function. It is the code that makes all the LEDs blink together. We will just copy this code. Make sure you have deleted it from the loop function. Don't worry about the code for the second pattern. We are going to leave this as it is. Now, move back to our newly created function. And then paste the code here. That's it. Your function is now ready to roll. And when you use this function, all the LEDs will blink together with a 300 millisecond delay. Now, we have completed the first step of creating a function. Now, let's move on to the second step, call the function. To call a function means to start using it. You can call the function anywhere within the setup or loop. All you need to do is copy the function's name along with the parentheses. And then, paste it inside the loop function. This is the same place where we deleted the code earlier. Before going further, let's take a quick test by uploading the code to the Arduino. As you can see, the two LED patterns are still working, even though we have removed the LED blink code from the loop function. This is due to the function we have created. Now, let's understand the inner working of the function. This will give you the idea about what's happening behind the scenes. To understand the working of the function, I have put all the code in the debugger. Now, let's run the code step by step. The microcontroller starts executing instructions from the beginning of the setup function. After that, it moves on to the loop function. Inside the loop function, the very first instruction is our function. This instruction tells the microcontroller to go inside this function, execute all the instructions within it, and then return back. Let's click on the Step Over button to see what happened. As you can see, the microcontroller is now inside our function. Here it will execute all the instructions one by one. The microcontroller is very fast and it only stops at delay function. Otherwise the instructions without delay will execute very fast, you cannot even see it. Now we have reached at the end of the function. From here, the microcontroller jumps back to the loop function, as you can see. It then continues executing the statements after our function, the ones related to the second pattern. And after executing the remaining statements in the loop, the microcontroller again jumps at the top of the loop. And from here, it will again jumps to our function, and this cycle continues until you power off your Arduino. Now, you have the basic idea about how functions work. Now let's explore the true magic of the functions. So, First we will create a new function. Let's name this function as patron2. Remember, always use descriptive names for your functions. Instead of writing new code for this function, we will reuse the existing code from the loop function. So, just copy the code, and then remove it from the loop function. Now, we have only one function remaining inside the loop. Let's move back to our newly created function. And paste the copied code here. That's it, the function is ready. Now we have two functions to play around. The first one is blink all LEDs, which we have created earlier. And the second one is patron2. To add additional LED patrons in this code, I have already created a third function. I have named this function as back and forth. It makes the LEDs blink in both the forward and backward directions. This adds a neat effect to our project. So, feel free to experiment and have fun with these functions. To make different LED chaser patterns, we will call these functions from the loop function. We will start by calling the blink all LEDs function 3 times. This will make all the LEDs blink together. After that, we will call the pattern2 function 1 time. This will turn on the LEDs one by one, and then turns them off in the same order. Then, we will use the blink all LEDs function again, to blink all the LEDs 3 more times. Finally, we will call our third function, the one that makes back and forth pattern. Now the code is ready. If you look at the loop function, it looks much simpler now. There is a very little code inside the loop function, and it is easy to understand and manage. This technique helps you effectively handle a large volume of code, making it more manageable, even for beginners. Now, it's time to upload this code to the Arduino board. Now look at the LEDs closely. These should blink using 3 different patterns. To enhance the blinking effect, I have adjusted the delay between blinks to 200 milliseconds, making it a bit faster and smoother. That's all about the functions. Now, let's move on the next section. In this section, we will explore an exciting tool in the Arduino IDE, called Serial Monitor. It is a powerful tool that allows communication between your Arduino and your computer. It enables you to monitor the sensor values in real time, directly on your computer screen. The best part is, it works in both ways, so you can exchange data between your computer and Arduino. This tool is particularly useful for finding and fixing issues in your code. Let's write some code to kickstart the serial communication with your computer. First, in your Arduino sketch, you will need to add the serial.begin function. This function is responsible for starting the serial communication. Now, you might wonder about the number inside the parentheses. This number is the speed at which your Arduino communicates with the computer. It is also called baud rate. The standard speed is typically set to 9600. In simple terms, this line of code tells the Arduino to start communication with the computer at a speed of 9600. After establishing the serial communication, you can use the serial.println function to send data from your Arduino to the serial monitor. Let's give it a try. In this example, we'll send a simple hello world message to the serial monitor. Inside the println function, I've written the text hello world within double quotation marks. In programming, when you want to print text, you always need to write it within the double quotation marks. Now, let's test the code by uploading it to the Arduino. The code is uploaded, and to check the output, you need to open the serial monitor. You can open it from the Tools menu by clicking on the Serial Monitor option. You can also open the serial monitor from the top right corner by clicking on this button. Here is a keyboard shortcut for the lazy ones like me. Press Ctrl plus Shift plus M from the keyboard, and it will open the serial monitor quickly. Here, First you need to select the baud rate, which is 9600. Since we have set the baud rate to 9600 in our code, it's required to match it in the serial monitor as well. If you select a different baud rate, you may see unexpected or garbage data in the serial monitor. Now, take a look at the output in the serial monitor. It's just as we expected. The Hello World message is beautifully displayed on the screen. That's a quick introduction of the serial monitor. And we will use it a lot in the upcoming sections of this course. Now, let's move on to the next section of the video. In this section, we will learn about the variables. A variable is like a container that holds information or data. Think of it as a labeled box where you can store different types of data. You can create a variable in two simple steps. First, define the data type of the variable. And then, give your variable a name. With these two steps you can create different types of variables. Let's create our first variable. First, we will define the data type of the variable. Here, the term int is a keyword. It tells the Arduino that we are using the integer data type. Integer is a data type that is used to store whole numbers. A number with no decimal point is called whole number. However, if you want to work with decimal numbers, then you will need a different data type, called float. A number with decimal point or fraction is called float number, or decimal number. Next, give your variable a name that not only makes sense, but also effectively represents the type of data it will hold. I have set the variable name as variable1. This name acts like a label on your box. Remember, spaces are not allowed in variable names. Now the variable is ready to hold values. Since we did not store any value in the variable, so the variable will automatically set to a default value, which is usually 0. Let's confirm this with a quick test. To observe the value stored in a variable, you can use the serial.println function. You just provide the variable name inside the parentheses. This will print the value of this variable on the serial monitor. As you can see, even if we haven't assigned a value, but still it's showing the value 0. This is because Arduino automatically sets its default value to 0. Next step is to store data into the variable. The process of storing data into a variable is called initialization. This is like putting things into your labeled box. Let's say if you want to store the value 50 in the variable. Then you can write variable1 equals 50. This statement will store the value 50 in the variable. You can also assign a value when you create the variable. You can do this by putting the equal sign at the end of the variable name, and then enter the value that you want to store in the variable. Now, let's upload the code and observe the value in the serial monitor. As you can see, the value is displayed correctly. This way you can effectively store and display values using variables. Next, let's explore a special type of variable called constant. You can create a constant in one simple step. You just use the const keyword when you create the variable. And this will convert the variable into a constant. Think of it like a box where you can place a value, but once that value is inside, it's locked and you cannot change it. After creating a constant, if you try to change its value, then the compiler will gives you an error message. It looks like the one shown in the console. Constants are great for storing unchangeable values, such as pin numbers. Pin numbers remain fixed throughout the program execution. It ensures the security of your data. So the constants are very useful when you want to keep some data read-only. Now, let's talk about another important concept about variables, called scope of a variable. Scope refers to the area of your code, where a variable is visible and can be used. You can imagine it as the boundary of your variable. For example, if you create a variable inside setup function, then it can only be used inside the setup. If you try to use this variable inside another function, such as loop, then the compiler will give you an error message. This error tells you that you cannot use a variable outside its scope. The same way, if you define a variable inside the loop function, then it can only be used within the loop function. However, if you want to use a variable across your entire code, then you can place it at the beginning of your code. This kind of variable is known as global variable, and you can use it anywhere in your code, including the functions. Now, you have idea about the variables. Let's take a closer look at the different data types that Arduino offers. Let's begin by exploring the Boolean data type. Imagine it as a switch with only two positions, true or false. This simplicity allows you to store only two values within it, which correspond to either 1 or 0. In programming, we use Boolean variables for decision making and checking conditions in our code. Next, let's explore the byte data type. Think of it as a small container designed for holding integer data. It has a limited capacity. It can hold values in the range of 0 to 255. This type of data storage is particularly handy for tasks that involve smaller numbers, such as storing pin numbers. For example, Arduino Uno has 21 GPIO pins, and the byte data type can efficiently manage these pin numbers without unnecessary memory usage. Let's move on to the int data type. Int stands for integer, and it is used to store whole numbers. Think of it as a medium-sized container, which is designed to store integer data. This capacity allows you to store data from around -32,000 to +32,000. This is suitable for handling a variety of everyday numbers in your projects. Now, when you need to work with very large numbers, the long data type comes to the rescue. The long data type acts as a larger container. It can store values up to around 2 billion, which is quite a lot. Next in the row is float data type. This data type is specifically designed for storing real numbers, which include decimal points or fractions. It is used for accurate and precise measurements that involves quantities which are not whole numbers, such as temperature readings or sensor values. The next one is double data type. Double is similar to float, but it can handle even larger real numbers. If you need to deal with very precise measurements or calculations, double can be your choice. The last one is character data type. It is used to store individual characters, like letters or symbols. When working with the character data type, it's important to remember that you need to enclose the character within single quotation marks. Let's understand another important concept called garbage value. This is an error in your code that the compiler is unable to identify. So it will not show any error message in the console. Such errors fall under the category of logical errors. Since the compiler cannot catch these errors, they often lead to unexpected outputs in your program. Let's explore it further with an example. Here, we have an integer variable in which we store the value 4000. And if we multiply this variable by 10, then the correct answer should be 40,000. However, when we execute this statement, the result isn't what we expect. Instead of 40,000, the variable holds some unexpected data. This issue is called garbage value. As we have learned earlier, an integer variable can hold values up to around 32,000. So, if you try to store a bigger number than its capacity, then it gets confused and gives you a garbage value instead of the number you want. To solve this issue, make sure to use the right data type for your number. This way you can avoid garbage value. Next, in Arduino programming, we have special symbols called mathematical operators that help us to perform calculations on variables. These operators include addition, subtraction, multiplication, and more. Let's dive in and see how they work. To understand the working of these operators, I have already created a simple program. And I am running this program using the debugger. Here we have created 3 integer variables. And we have stored some default values inside these variables. Let's have a look at the current values in the variables. Variable 3 holds 0. Variable 1 is set to 15, and variable 2 holds the value 2. First, the microcontroller will add the values of the variable 1 and variable 2. And then, it will store the result, which is 17, into variable 3. Let's execute this instruction. Now if you look at the variable 3, it has 17. The same way, we will go step by step. We don't need to cover these in detail again. But if you look at the division, the variable 3 ends up with 7, but the real answer should be 7.5. This is just because the integer data type is designed to store whole numbers, so any decimal portion will be deleted automatically. So, if you need answer with decimal point, then you can use float variable. It allows us to keep the fractional part. Next, the modulus operator gives us the remainder after division, so the variable 3 will have the remainder value, which is 1. Next, with the increment operator, the microcontroller adds 1 to the current value. So the variable 1 will go from 15 to 16. On the other hand, the decrement operator subtracts 1 from the current value. So, the variable 2 will go from 2 to 1. Now we have a clear understanding of how operators work, and how they affect data stored in the variables. Next, let's explore another type of operators, called relational operators. They are used to specify the condition in the program. These operators compare two values, and gives a simple answer, true or false. So it is best for specifying the condition in the program. In C language, there are several relational operators. These operators help us to understand relationships between values. Let's understand how they work. The first one is the greater than operator. It gives true if the value on the left side of the operator is greater than the value on the right side. Otherwise it gives false. As you can see, the value 10 is on the left, and 20 on the right side. Since 10 is not greater than 20, so the result will be false. The other operators also work in a similar way. You can just test each condition, and see if you get true or false value. It's like asking questions to your Arduino, and getting simple answers. Let's explore another example to better understand the concept. In this example, we will focus on the less than and equals to operator. This will gives true if the number on the left is smaller than or equal to the number on the right. However, if the number on the left is not smaller or equal, then this operator will return false. In our case, both numbers are same, and they are equal. Now, since the operator checks for both being smaller and equal, so it will return true, because 1 is equal to 1. That's all about the relational operators. They help us to compare numbers and make decisions in programming. Let's move to the next section of the video. In this section we will discuss about loop. A loop is a helpful tool in programming that allows you to execute a block of code repeatedly for a certain number of times. It's like telling the Arduino to do something over and over again. There are 3 types of loops: the while loop, the do-while loop, and the for loop. Among these, the for loop is a popular choice for programmers, because it's quite flexible. So, let's focus on understanding the for loop. If you understand it correctly, the other loops will become simpler for you. The for loop consists of 3 main components: initialization, condition, and increment. Let's break down the structure of the for loop step by step. First, we have the initialization part. Here we set a starting point for the loop. We will start the loop from 1. To set the starting value, we will use a variable. Let's name it to I, and we will set its value to 1. It's like telling the Arduino to start counting from 1. Then comes the condition. Here you need to specify how many times the loop should run. Let's say, we want to repeat the loop for 5 times. So we will set the condition to I less than equals 5. This condition will be checked before every iteration of the loop. As long as the condition remains true, the loop keeps running. Let's move to the increment part. After each iteration of the loop, it increments the value of the I variable by 1. It is used to keep track of how many times the loop has run. Finally, we have the loop body. This is where we place the actual code that you want to run over and over again. In this example, we will just display the value of the I variable on the serial monitor. Now the loop is ready. Let's understand the working of the loop. The loop's journey begins with the initialization part. In this step, the microcontroller determines the starting value of the loop, which is set to 1 in our example. It is important to note that the initialization part runs only once at the beginning of the loop and won't repeat. After that, the loop checks the condition. In our case, 1 is less than 5, so the condition is true. As a result, the microcontroller moves into the loop body. Inside this body, it executes our instruction, which just displays the value of the I variable on the serial monitor. And then there comes the ending curly bracket. It indicates the end of the loop. From here, the microcontroller jumps back to the start of the loop. Now it comes on the increment stage. Here it will set the value of I variable to 2. Next, the condition is checked again. Since the 2 is less than 5, so the condition is true. Now, the loop enters into the body again. This time it will print the new value of the I variable on the serial monitor. This way the loop runs for 5 times. After completing the 5th iteration, the value of the I variable is now 5, and increment operator increase it to 6. And then the condition will check again, for the final time. At this point, the condition is false, because the 6 is not less than 5. So, the microcontroller skips the loop body, and jumps at the end of the loop. Let's give it a try by uploading it to Arduino. As you can see, the serial monitor displays the numbers 1 through 5, one after the other. What if you want to run the loop in opposite direction? Here is a simple trick. This time we will start the loop from 5. And it ends when the value of the I variable becomes less than 1. And finally, decrease the value of I variable by 1 using decrement operator. With these changes the loop will run in the opposite direction. Here you can see, now the serial monitor displays the numbers in opposite direction. And there you have it. This is the simple introduction to the for loop in Arduino. Next, let's create a simple project to explore the power of loops. In this project, we will learn how to control the brightness of an LED using a technique called PWM. Pulse width modulation is a technique to create analog-like signals using digital pins. As we have discussed earlier, the Arduino board has 6 digital pins that support PWM. These pins help us to generate varying voltages between 0 and 5 volts, which is useful for controlling the LED brightness. It is important to note that PWM technique only simulates analog signals, and it cannot produce real analog signals. To generate a PWM signal, we will use a special function called analog write. This function requires 2 arguments. The first one is the pin number that you want to control. And second one is a value between 0 and 255. This value tells the Arduino how much power you want to send to the connected component. If you will use the value 0, it's like telling the Arduino to give 0 power to the pin. And if you send 255, then full 5 volt of power will send to the pin, which will turn on your component at full power. So, if you will use the value 128, it means you are sending half power, so the component will drive with half power. This is like using a dimmer switch for a light. It's not super bright, but it's not completely dark either. So it will remain in the middle. Let's understand it with a simple example. First, look at the wiring diagram. Here, we have connected an LED to pin number 9 on the Arduino, which is one of the PWM pins. And we are going to control the brightness of this LED using the analog write function. Let's move to the coding part. First, we will define a constant variable to store the pin number for the LED, which is connected to the pin number 9 on the Arduino. Then, in the setup function, we will set the LED pin as an output, using the pin mode function. This step tells that we are going to control this pin. And then, in the loop function, we will use analog write function to control the brightness of the LED. The analog write function takes two parameters. The first one is the pin number, where the LED is connected. And the second parameter is a value between 0 and 255. Let's start by turning off the LED completely, by setting the value to 0. When the value is 0, it means we are sending 0 volts to the LED. It will turn the LED off. After turning off the LED, we will add a delay of 500 milliseconds. This delay will keep the LED off for half a second. Next, we will use the analog write function again, but this time we will set the value to 128. This will send 2.5 volts to the LED, to make it half bright or dim. After turning off the LED, we will add a delay of 500 milliseconds, to keep it off for half a second. Next, we will use the analog write function one more time, but this time we will set the value to 255. This time we are sending 5 volts to the LED, so the LED will fully bright. Finally, we add another delay, to keep it fully bright for half a second. Now let's upload the code to Arduino, and observe the LED behavior. As you can see, the LED starts from the off state, then after a 500 millisecond, it becomes half bright, and after another 500 milliseconds, it becomes fully bright. Next, let's explore how to use the analog write function with a for loop, to create a smooth LED fading effect. As we have discussed earlier, the PWM values have a range from 0 to 255. So we will start the loop from 0, and we will run it for 255 times. To start the loop from 0, we have set the initial value of I to 0. Then we have set the condition, I is less than or equal to 255. This condition will run the loop for 255 times. Then we will use I++ to increment the value of I by 1. Then, inside the body of the for loop, we will use the analog write function to control the LED brightness. The first argument will be the pin number, where the LED is connected. And the second argument will be the value of I. During each cycle of the loop, the variable I is incremented by 1, this way the loop go through all the numbers from 0 to 255. As the value of I increases with each cycle, the analog write function will send higher voltages to the pin, making the LED brighter more and more. To make a smooth LED fade effect, we will add a 10 millisecond delay after each cycle of the loop. Now the code is ready. Let's give this a try, to see how it works. As you can see, the LED is currently fading smoothly from off to on, but it turns off immediately. So, if you also want the LED to turn off smoothly, then we can do this by adding a second loop in the code, and running it in the opposite direction. To save time and effort, we will make a copy of the existing loop. To run the loop in opposite direction, we will start it from 255, and this loop will continue as long as the value of I remains greater than 0. And finally, we will set the counter variable to I minus minus. Now we have two loops. The first loop will gradually turn on the LED, and the second loop will gradually turn it off. So it will create a cool LED fading effect. Let's upload the code to check it's working. Now, look at the LED. As you can see, the LED smoothly turns on, and then gradually turns off, creating a pleasing fading effect. That's all about the analog write function. Let's move to the next section. In this section, we will learn about the digital read function. This function is used to read digital input in your Arduino projects. The digital read function requires just one parameter, which is pin number. Here you will need to enter the pin number you want to read the state. If it reads the 0 volts on the pin, then it will return low, and if it reads the 5 volts on the pin, then it will return high. Let's make a simple project to understand the working of digital write function. First, look at the wiring diagram. Here we have connected a push button to the pin number 8 of Arduino. Now, we will use the digital read function to determine whether the button is pressed or not. First, we will declare a constant variable called button pin. Here we will specify the pin number to which the button is connected. In the setup function, we will set the button pin as an input pull-up using pin mode function. The input pull-up is used when you're working with buttons. Button is a simple component that closes an electrical connection when pressed. But when it is not pressed, then the status of the pin can be uncertain. This means the pin is neither high nor low. To solve this issue, we use a pull-up resistor. It keeps the pin high when the button is not pressed, and when you press the button, it will turn the pin into low. As the Arduino has internal pull-up, so no external resistor is needed. By setting button pin as input pull-up, we activate this internal pull-up resistor. This helps us to reliably detect the button presses in our Arduino code. Next, we initialize the serial communication at a baud rate of 9600. This will help us to display the results to the serial monitor for debugging purpose. In the loop function, we will define a Boolean variable called button state. It will be used to store the current state of the button. Then, we will use the digital read function to read the current status of the button connected to pin number 8. If the button is pressed, then this function returns low, and if the button is not pressed, it returns high. And this value will be stored in the button state variable. And then, we will use the serial.println function to display the current state of the button in the serial monitor. Finally, we will include a delay of 100 milliseconds to make a short pause between readings. This helps us to avoid any issues caused by button bouncing. Now, let's upload this code to the Arduino board and open the serial monitor to see the results in action. Now, if you look at the serial monitor, it's displaying 1. It indicates the current voltage on the pin is 5 volts. So it means the button is not pressed. Let's press the button to see what happens. As you can see, the serial monitor is now displaying the value 0. It indicates the current voltage on the pin is now 0 volts. So it means the button is now pressed. This way you can read digital inputs in your Arduino projects. Now, it's time to take the next step and dive into controlling an LED using this button. But before going further, let's explore about the if statement. The if statement is a fundamental concept in programming. It is used for making decisions in the code. The if statement consists of two main parts. The first one is condition, and the next one is body. The if statement first checks the condition. If the condition is true, then the statements inside the body will be executed. However, if the condition is false, then the code inside the body of the if statement is skipped, and the program moves to the next line after the if statement. After the if block, we have some code that is outside of it. This code will always execute, regardless of whether the if condition is true or false. Now, we understand the if statement. Let's take a step further with the if-else statement. The if-else statement has two blocks. The first one is if block, and the other one is else block. The if-else statement allows us to execute one block of code when the condition is true, and another block of code when the condition is false. The working of the if-else statement is very simple. First, the condition is checked. If it is true, then the code inside the if block will execute. And if the condition is false, then the code inside the else block will execute. So, the both blocks will never run together. Only one block gets executed, and it will depend on the condition you set. That's all about the if statement. Now, it's time to write some code to control the LED using a push button. First, let's have a look at the wiring diagram. Here the LED is connected to the pin number 11. And the push button is connected to the pin number 8, same as before. Now, let's move to the coding part. This is the same code that we have written before, to display the button state in the serial monitor. Here we will declare another constant variable, to specify the pin to which the LED is connected. In the setup function, we will set the LED pin as an output, using pin mode function. This step tells the Arduino that we want to control this pin. In the loop function, we have already some code. It reads the state of the button using the digital read function, and stores it in the button state variable. And below this line, we will use an if statement to check if the button is pressed or not. When the button is pressed, its state will be low. And when the button state is low, then the condition will become true, and the code inside body will execute. So inside the body, we will turn on the LED by setting its pin to high, using the digital write function. And then we will add a delay of 100 milliseconds, to handle the button debounce. However, if the condition is false, then code inside the body of the if statement is skipped, and the program moves to the next line after the if statement. Here, we will just turn off the LED by setting its pin to low. Now the code is ready. Let's upload it to Arduino. Now, if you look at the LED, it is currently off. Let's press the button to see what happens. As you can see, when the button is pressed, the LED turns on, and when the button is released, the LED turns off. You can also configure the button to toggle the state of the LED. This means, when you press the button for the first time, the LED will turn on, and when you press it a second time, the LED will turn off. You can do this with a single change in the code. First, we no longer need this digital write function, so we will remove it. Now, let's focus on the digital write function inside the if statement. Instead of using the high value directly, we are going to do something cool. We will use the NOT operator with the digital read function to toggle the state of the LED. Then we will provide the LED pin as the parameter of the function. Now we have set this function to read the voltages on LED pin. Now, let's talk about the NOT operator. NOT operator is used to invert a result. If the result is true, then it will turn it into false, and if the result is false, then it will make it to true. Now, let's put these together. First, the digital read function will read the voltages on the LED pin. For example, if the LED is off, then the digital read function returns false, but the NOT operator will make it to true. In Arduino programming language, true means high. So the LED will turn on. The same way, if the LED is on, then the digital read function returns true. But the NOT operator will make this value to false. And false means low, so the LED will turn off. Now the code is ready. Before uploading the code, we will just increase the delay to 500 milliseconds. This will just increase the delay between each button press. Now, click on the upload button to upload the code to Arduino. Let's press the push button to see the working of the project. Here you can see, when we press the button, the LED switches between on and off, like a little digital dance. That's all about the digital read function. Now, let's move to the next section. In this section, we will learn about analog inputs. The Arduino board has 6 analog pins. These pins are labeled from A0 to A5. Unlike digital pins that can only read high or low signals, analog pins can read a range of values. To read the analog values, we will use a function called analog read. This function just requires one parameter. It is the pin number from which you want to read the data. This pin number corresponds to the analog pin, where your sensor is connected. This function returns a value within a range of 0 to 1023. Here, 0 represents 0 volts, and 1023 represents 5 volts. To read the analog data, we will use a sensor called Potentiometer. This is a simple analog sensor that acts like a variable resistor. As we turn the knob, its resistance will change, and we can measure that change using analog read. First, look at the wiring diagram. Here, we have connected a potentiometer to the analog pin, which is labeled as A0. Now, we will write some code to read values from the potentiometer. First, we will define a constant variable to store the analog pin number we are using. In the setup function, we will start the serial communication for monitoring the results. And then, in the loop function, first, we will create a variable called pot value. This variable will be used to store the analog readings from the sensor. To read the values, we will use analog read function. This function requires just one parameter, which is the pin number where the potentiometer is connected. Analog read function will read a value from the potentiometer and then store it in the pot value variable. Next, we will use serial.println function to display the value on the serial monitor. Now the code is ready, it's time to upload it to Arduino board. After uploading, open the serial monitor to observe the values received from the potentiometer. Let's turn the potentiometer knob. As you can see, the values in the serial monitor are changing. These values represent analog readings from the sensor. The minimum value is 0, and the maximum value is 1023. This way you can collect data from any analog sensor using Arduino. Now, let's make a project. Here, we will use a potentiometer to control the brightness of an LED. First, take a look at the wiring diagram. Here, we have connected an LED to the pin number 9, which is the PWM pin. As we discussed earlier, the PWM pins are used to control the brightness of an LED or the speed of a motor. Additionally, we have connected a potentiometer to the analog pin, just like in our previous project. Now, let's move to the coding part. Here, first we will define a variable to store the pin number of the LED. Next, in the setup function, we will use the pin mode function to set the LED pin as an output. As you have noticed, we have not set the potentiometer pin as an input. This is because all the pins on Arduino are configured as input by default. Next, in the loop function, we have used the analog read function to read the value of the potentiometer. And we have stored this value in the variable called pot value. This variable will play an important role to calculate the brightness of the LED. As we rotate the knob of the potentiometer, the value of the variable will change, and we will use it to control the brightness of the LED. However, there is a small challenge here. The analog read function returns values within the range of 0 to 1023. However, to control the brightness of the LED, we need analog write function which works with PWM signals. PWM works in the range of 0 to 255. This means we have to convert the analog values into a suitable range of PWM values. To solve this problem, Arduino language provides a function called map function. Let's see how to use this function. First, we will define a variable to store the converted value. We have named it as fade value. Now, we will call the map function to convert the analog value to the PWM value. This function requires 3 parameters. The first one is the value that you want to convert. In our case, it will be the pot value. This variable will hold the most recent value as you rotate the knob of potentiometer. The second parameter is the source range. For the analog sensors, this range is from 0 to 1023. The third parameter is the target range, which is the PWM range of 0 to 255. Now, when this function will execute, it will convert the value of the variable to the range compatible with the PWM. And the resulted value will be stored in the fade value variable. Now comes the exciting part. Here we will use the analog write function to control the brightness of the LED. This function takes 2 parameters. The first parameter will be the pin number, where the LED is connected. And the second parameter will be the fade value. By adjusting the fade value, you can control the brightness of the LED. Now the code is ready, let's give it a try. As you can see, when we rotate the knob, the brightness of the LED changes accordingly. So this way, you can read analog inputs and control digital outputs. Congratulations, we have reached at the end of this Arduino programming course. Throughout the course, we have learned about controlling the analog and digital signals, and we have made some simple LED controlling projects. These are the building blocks to create the real-world applications. We hope this video course has provided you with the confidence to explore the endless possibilities in Arduino programming. Thank you for joining us on this educational adventure. Happy coding, and may your journey be filled with innovation and success. Bye.